Hi everyone, and welcome to Lecture 5 of the Reliable and Interpretable Artificial Intelligence course taught at ETH Zurich. My name is Martin Vecev and I'm a professor at ETH. And this Lecture 5 is going to be about neural network certification with complete methods. So if you recall last time, we went over the classification of the different verification techniques into complete and incomplete methods, as well as sound and unsound techniques. And we introduced one of the more simple incomplete automated certification methods, the box convex relaxation. So if you are forgot some of these concepts, you should probably take a look at the prior lecture 4. So today we're going to be focusing on complete methods. So if you remember, complete methods means that a complete verification method is one where if the property holds, then the method will be able to prove it upon termination. Okay. Specifically, we're going to be focusing on a complete verification with MILP, which stands for Mixed Integer Linear Program. And so these programs are solved with what is typically referred to as MILP solvers, right? And so how does MILP work? We're going to how to use MILP in order to solve the neural network certification problem we're going to study in this lecture, right? And so for ReLU networks with consisting of affine layers and ReLU layers, MILP certification is complete, right? And now the problem with MILP is, so the benefit is that it is complete. So if, for example, robustness holds for the particular point we are trying to prove it for, like an image, the MILP will be able to, a MILP solver should in theory be able to prove this property. The downside of MILP is that it is expensive. So MILP, reduces to some branch and bound together with solving linear programming instances, which are at least NP complete. We're going to see also where an additional exponential blowout comes when we're generating these LP instances. So that's one of the downsides, and this is also the reason why, while attractive because of the completeness property, MILP solvers typically do not scale to very large networks. And so an interesting area of research is how to combine these complete methods based on MILP with incomplete methods based on some of the convex relaxations we're going to be studying in the course. For example, the box or the interval convex relaxation, which we looked at the last lecture, right? And so what we're going to see in this lecture, we're going to see how to use MILP to solve the neural network certification problems, which is typically applied to small or medium networks. And then we're going to see how to improve the performance of MILP, to scale MILP a bit more by using the box convex relaxation. And this box domain, this box abstraction that we looked at last time is going to help MILP do less work, the MILP solver to do less work, and so it's going to be faster in proving the property, or in finding a violation if the property does not hold, right? So MILP is also MILP solvers are also sound. Of course, we're going to show the combination with the box here, with the box abstraction, the box relaxation, but other combinations are also possible with more expressive abstractions, which we'll see later in later lectures. All right, so let's take a look now at the MILP encoding. How would you actually encode the, first the generic MILP problem definition, how we express problems, and then to see how would actually encode a neural network consisting of affine layers and of ReLU layers into a MILP as a MILP instance. So let's use our drawings as we usually do. Okay, so let's first look at the MILP generic problem definition that we're going to be using later. We're going to be instantiating this method later. So what we have here is we have this expression, we have this function, which is this linear expression here, which is called the objective. Okay, so this would be some expression which we are trying to optimize for, like optimize its value, find assignments to these continuous variables x1, x2, xn, so that the given expression is maximized or minimized. Here we're going to be looking at minimization. Okay, so we have some objective here, some linear objective. And then what we want to do is to find some values for x1 to xn, where the objective is minimized, subject to some constraints, right? Subject to some linear constraints, some polyhedral constraints over here, and you can write down a bunch of these constraints, which together constrain the values that the variables x1 to xn can take. So you can write these constraints here, and this would restrict the possible solution space for x1 to xn. Right. In addition, you can also provide box bounds or interval bounds for the continuous variables like this. Okay. So for each variable xi, we can provide a lower bound li and upper bound ui. So this would be concrete values. That xi should be in this range. Now, because this is a mixed problem, right? In addition to continuous variables, we're also allowing integer variables. So some of these xi's that we see here actually may end up as integers, right? So we can also mix both real values and integer variables in this formulation, right? So this here is the type of the variables, right? So Ci, Ai, J, and Bi are reals, Lu are vectors and dimensional vectors, and so Li and Ui are also reals, providing these bounds. Okay. Now this xi's here or xj here that we used, okay, these are integers. In our case, when we are going to be encoding the neural network verification problems, they're even going to be simpler. They're just going to be binary. So they're just going to be, as we'll see, they're just going to be taking on the values between 0 and 1. And because they can be integers, or in our special case binary, we have a mixed integer problem where some of the variables are reals and some of the variables are integers. And there is a bunch of different mixed integers MUP solvers, right? Grob is one of the solvers, right? And this is one of the solvers that we sometimes use to solve these MUP problems, but there's other solvers like GOPK and different ones. This encoding that we're going to be looking at appeared in a ICLR paper that you can take a look. It's actually in the appendix of the paper, so you're welcome to to take a look there and to see further if you like to see more details of the encoding. But what's in the lecture should be sufficient to cover what we need for the course. Okay. So let's move on and see how we're going to be specifying the neural network certification problem as a MILP instance, right? One thing to notice here is that here, MILP doesn't really talk about verification or certification. It just talks about optimization. So we need to have a way in which to convert this certification or verification questions into an optimization problem. And so we need to see how to do this. Okay, so let's move on. Right. So here is going to be the 4 steps that we're going to be following in encoding the neural network certification problem as a MILP instance. So we're going to be encoding the affine layer. So we're going to do them in this order, 1, 2, 3, 4. But you have to do, all the steps, right? The steps are actually not dependent on each other. You just have to do all of this, encode all of these pieces here. So first, we're going to show how to encode the affine layer, right? The affine layers that the neural network may be using. We're going to show how to encode then the RELU layer, right? That's a little bit more involved. Then we're going to show how to encode a precondition, for instance, the L infinity box that is placed around the input, and or it could be some other precondition, right? And then we're going to show how to encode the postcondition psi, and here we're going to capture this. We're going to see this conversion between from certification to optimization. So let's see how we encode the affine layer in the MIOP instance. So the affine layer is a fairly very direct because it is just a linear constraint, right? And so you can just encode it directly it just fits directly into the MIOP. There is not really MIOP instance. There is just not really need to do anything more here except just directly encode the computation in MIOP. And here are the weights of the edges as we've seen in our network, and B is the bias associated with the particular neuron. Okay. And you can look at the paper that I pointed before. Convolution it also can be encoded fairly directly, similar to how we encode the affine layer. Okay, so encoding the affine layer is very direct with MIOP. It's exact encoding directly. Now let's see how to exactly encode the RIAI layer, and this is a little bit more involved. So we'll spend a little bit of time here. So this is going to be encoded. So let's first get back to let's use our drawings here. So if you remember, the RIAI activation takes as input the neuron X and produces the value Y, where Y is the maximum of, so if X is negative, and then this just takes the maximum of 0 and X, right? So if X is negative, then the Y becomes 0. If X is positive, then the Y becomes X, okay? Okay, so let's look at the encoding and get a little bit of intuition behind this encoding, because that's what's important here. So we're going to have 4 constraints that we're going to be using to encode the RIAI. And I should mention to you that there is other encodings, but this encoding is actually quite effective. Okay, so the first constraint places a bound on Y. So all of them are going to be placing a bound on Y, adding constraints for Y. But at the same time, you're not just constraining the Y, you're also constraining the X here, right? So the first one, Y is less than or equal to X minus L. We have to see what L is times 1 minus A. Now, this A, if you remember, we said that the MIOP instance consists of both real valued variables as well as integers. And so the integers here are going to be these A's, right, which are associated with every RIAI activation in the network. So it's just going to be able to take 2 values, 0 or 1, right? So you can actually play with this a bit to see what would you get. For instance, if A is 1 here, you'd end up with 0 over here for this term. And then you're going to end up with Y is less than or equal to X, but Y is also greater or equal to X. So you're going to end up with Y is equal to X. And Y is greater than equal to 0, and Y is less than or equal to U times A. So now what is this L and U business here, right? So what are those? Like this L and this U. Okay, and this is where the precomputation with an incomplete method helps the encoding a little bit, right? So here what we have, this L and U are just the bounds, the lower bound and the upper bound that we have computed for the input neuron X, right? So for instance, we may have executed the box analysis, the box processing of the input, and for a given neuron X, we may have determined that X is in the range -2 to 2, for instance. And then we would know that L is -2 and U is 2, right? So we're going to use this incomplete method, not for verification, but we're just going to use it to compute these bounds L and U that the different neurons can take, right? And so if you want to think of it in another way, once we compute those bounds, we are going to be using it to as a basis to compute even tighter bounds using the MIOP instance and then the subsequent MIOP solver. Okay, right? If we were on the board in class, we would actually go over this with several examples, but I have actually written it by hand and then to show you, to discuss a little bit this encoding on an example so that you can get an idea. But you can already get a bit of intuition by just plugging values for A0 and A1 and seeing what happens actually. And intuitively, what will happen is for the different values for A0 or A1, you're going to generate linear programming instances, LP instances. So if you pick, as we said, 1 here, you're going to end up with y is less than or equal to x. And this is going to be one LP instance. If you pick a is equal to 0, you're going to end up with y less than or equal to x minus l, y greater than or equal to x, and all the other two constraints. And this is going to be the other LP instance. And so this is what we are going to examine right now to get a little bit of an intuition behind these encodings and to see why this is actually sound and correct thing to do. All right, so let's look at a drawing here, something that we would normally do on the board, but now we can do it here. Okay, so let's see. Okay, let me pick another color so that we can actually highlight and draw here. All right, let's just move it away from us over here. All right, so let's get a little bit of an intuition. And here on the right side, I have actually put the RIAI encoding so that we can look at it when we're doing the substitutions, and not so that we don't forget what we're looking at. So let's see, right, what the different instantiations of this branching variable A would actually give us here. What kind of linear programming instances could be generated by taking different values of A. So let's start here up top. So what we're going to get, let's take the case of A equal to 0 over here on the left, right, top left. So if A is equal to 0, we are going to get 1 minus 0, right here. So you're going to end up with y is less than or equal to x minus l, right? Y is less than or equal to x minus l, y is greater than or equal to x. Well, we just copy this. And then we're going to end up with some values for, right, for y here. So y here is going to be y less than or equal to u times a, but because a is 0, we're going to end up u times 0. So y is going to end up being less than or equal to 0. And last constraint, y greater than or equal to 0, we have just copied it. So this y less than or equal to 0, we just get by multiplying u times 0. So we get y less than or equal to 0. And so these together imply that, obviously, that y is actually equal to 0. All right, so one instance that we're going to get is a situation where y is equal to 0, right? And x, right? If you look at x, how x is partitioned, x is less than or equal to y, but y is 0, so x is going to be less than or equal to 0. And x is going to be greater than y plus l, just from this constraint over here. And so we're going to end up with x is greater than or equal to 0 plus l. And so x is greater than or equal to l. So from this instantiation here, we end up with the case where x is between l and 0 and y is 0, right? So this is this case. So this is supposed to capture, this is going to generate one LP instance. So this is like one LP instance here, one linear programming instance, this instantiating this branching variable a to 0, okay? Okay, so now let's look at the case a equal to 1, okay? So if you look at the case a equal to 1, so one thing before we look at the a equal to 1, you can already see when we look at a equal to 0, that if this L over here is a positive number, for instance, if L is 5, it would say that, x has to be greater than or equal to 5, and x has to be less than or equal to 0, so this would be unsatisfiable, right? So this linear programming instance here would be unsatisfiable, and there is no need to explore it further in the solving, okay? So this only makes sense if L is really less than or equal to 0, okay? So if L is negative, really, this makes sense, or not positive. Okay, so let's look at the other branch. What happens if we instantiate a to 1? So if instantiate a to 1, what are we going to get? We're going to get that 1 in this equation on the right. We're going to get 1 minus 1. This is going to be 0. So we're going to end up with y is less than or equal to x, while we have y is greater than or equal to x. So this is going to mean that y is x, right? We can, these two inequalities imply that y is equal to x, right? Then we have y is less than or equal to u times a. Well, a is 1, so we're going to end up with y is less than or equal to u. Okay, and then we know that y is greater than or equal to 0 after the real u, right? Because the y has to be non-negative. And so these two, the top ones imply that y is equal to x, and the bottom ones obviously imply that y is between 0 and u. Okay. Similarly to the previous case here, if u ends up to be negative, then this would be an unsatisfiable linear programming instance here, right? This is the constraints cannot be satisfied anymore because y is if u is negative. So this makes sense if the u is non-negative value. Okay. So this generates one linear programming instance if you pick a equal to 0, and if you pick a equal to 1, it's going to generate another linear programming instance. So if you have lots of ReLUs, right, if you have k ReLUs in your network, in your neural network, then you're going to have 2 to the k linear programming instances. 2 for the first one, 2 for the second ReLU, 2 for the, all the way to k, and so that you'd end up with 2 to the k. So obviously, if you can somehow early on show that some of an LP instance early in the branch is unsatisfiable, then it would save you a lot of time exploring the different linear programming instances that you need to that the solver would need to consider. Okay. So I hope this gives you a little bit of intuition. So just to get even more intuition, let's look at an example here for the different cases. All right. So let's look at the first case below 0, where the neuron x, right here, the input to the ReLU, okay, so this input x is in the range, some value, some negative value, -2 to -1. Okay, so if we have a situation where x is negative, strictly negative in some range, then if we instantiate the case a equal to 0, and we copy our equations, we are going to get that, if we do the calculations here, we're going to get that, well, we know that y is equal to 0. Okay, y is equal to 0, because that's what the ReLU does. And if we do the calculations here, we're going to see that the, x is in the range -2 to 0. But we know that x is in the range -2 to 1, -2 to -1. So this would be the tighter range that we would use. But this would be like an LP instance, that one instance that we would generate that the solver would explore. X would be in some negative range, and the y would be 0, and this would be a valid instance that it would generate, potentially satisfiable instance. Now, if a is 1, so in the case where x is negative, strictly negative like this in some range, and if a is 1, we, if you remember, if you look at the constraints up here on a is 1, you know that y is equal to x, so we know that y is equal to x, but we know that y has to be non-negative, right? So y needs to be between 0 and u, but the u is upper bound here of x is -1, so the u is -1, so you'd end up with y being between 0 and -1, because that's what we know from here. Okay, and so if y is in the range 0 and -1, it has to be greater or equal to 0 and less than or equal to -1 in this range, then this is clearly unsatisfiable. Okay, this instance is unsatisfiable. There's no way to find values here for y where this holds, and so in that case, the solver doesn't really have to proceed here further to explore this, because this would be unsatisfiable. But you would need to consider this case here, okay, where a is equal to 0. So why are we going through this? Just to get to the more interesting case at the end, case C, but let's go for case B. So let's consider the case where, just to be exhaustive here, let's consider the case where x happens to be positive, strictly positive in some range. In this case, it's 1 to 2. Well, again, if you do the instantiation here, let's say we take the instantiation a equal to 0, so we generate that linear programming instance, okay? then, well, we know that y is 0, right? We already derived this before early on. And we know that x should be between L and 0, where L is 1 here. Okay, so x should be greater than or equal to 1, and it should be less than or equal to 0, according to the, the branch here that we know we derive for x. And so, this is not satisfiable. So it cannot be greater than or equal to 1 and, less than or equal to 0. So this is unsat. Okay, so the solver would actually not proceed with exploring this case further. Okay. So now let's take a look at the other branch where a is equal to 1. So in that case, x is between 1 and 2, which we know. And if we do the math again, we're going to end up that y is in some range. Okay, but y is equal to x, so y is also in the range 1 and 2. This is just a more looser range, but this thing tightens it here to 1 and 2. So this instance here that we get, these constraints that we have, x is between 1 and 2, y is equal to x, y between 0 and 2. Well, y would be, you can derive that y is between 1 and 2. So this instance is potentially satisfiable, right? It can be satisfiable. It would be combined with other LP instances for other RIAIs downstream, but this is satisfiable, so you need to consider this one. So you need to consider this one in this case and this one in this case, depending on the value of x here. This is really a kind of a naive way that the solver would go about generating the instances that it needs to consider. This is just to give you an intuition for what happens and where the key point here is how does this lower and upper bound constraints help you. So it helps you because in some cases like here and over here in case A and case B, you can establish by using this L and U that the instances would not be satisfiable, and the solver can just not explore further. Or if you are writing the MIOP solver, you don't even have to generate those instances. You can just generate the instances where they're potentially satisfiable, right, over here. Okay, so now let's consider the more interesting case C, and we'll discuss a little bit why this is the most interesting case that governs essentially how expensive, it determines how expensive your certification is going to be. And so what we have here is we have the value of x is -1 and 2. So in that case, we refer to such a RIAI as a crossing RIAI. So the value of x crosses the 0. It can be both negative and it can also be positive, right? It can be any of these values. So it's not strictly positive, it's not strictly negative, but it can be there. So these crossing values, why are they interesting? Let's see. Well, let's instantiate the two LP instances, linear programming instances that would get in this case. So if we get, well, the case A equal to 0, we are going to end up with y0. Well, we know that. And then we're going to end up with the case, x is between L and 0. Well, L is -1 here. So we're going to end up with the case x is -1 to 0. And this looks like a potentially satisfiable LP instance, right? You can find values for x and y where the instance is satisfiable. But of course, combining with LP instances downstream, all the constraints may end up unsatisfiable. But for now, it is satisfiable, and you cannot discard it. It's certainly not unsat right here. Unsatisfiable. Unsat means unsatisfiable. Okay, in the case of A equal to 1, okay, we know that y is x from before, from our derivations up there on the top right over here. Y is going to be equal to x, right? And we know that y is between 0 and u, but the upper bound u here is 2, so we're going to end up with y is between 0 and 2. Okay, so this is also satisfiable here. And so we have to consider this case as well. So what you see here, and that's the important point to notice, there are 2 points. So first, one point we already said, the L and U, the lower and upper bound, that are computed via some incomplete method that is sound, like for instance, the box convex relaxation, it helps you prune, it helps you remove LP instances that are going to be unsatisfiable. That's point 1. And point 2 is that if you actually your L and U bounds, like here is the L, here is the U, right? If these are actually such that you are crossing the 0, then you have a so-called crossing RIAI, and then you have to consider both instances here. And so imagine that many of the values are crossing like that, you'd have a very exponential behavior. Essentially, you'd be considering all of the possible combinations of these values here, right? And so your certification problem would get it's exponential in the number of values that are crossing like this, and so that's why they say that and this is the point that we'll get to later, all the regularizations and all the provable training or certified defenses, they essentially try to in a sense bias the weights away from having this crossing situation like that to either be in the case A or be in the case B, because the more crossing behaviors you have like that, the harder it is to prove, because you're going to be generating more and more. The more crossing values you have, the more linear programming instances you're going to be generating, and your solver is going to choke. And so if you look at many of the provable training methods, they try to get you to have fewer crossing like this. And so when you see people talking about verification or verification scaling, it's not just important to look at the number of neurons that you have in the network, but also it's more important to look at the number of neurons where this crossing happens like this. So it's really, you may have a 100,000 neuron network, and you have 5 crossings, 5 arrays that cross, and then your verification is going to be really fast. And so make sure that you are aware of this crossing point, okay? So I hope this gives you a little bit of intuition about one, how the incomplete method can help produce bounds like LNU bounds, lower and upper values for the neurons, which allow you to prune some of the linear programming instances that would be generated otherwise by the MIOP solver. Right? And then also be aware of these crossing issues if actually, you cannot prove, if they really do cross like that, or you just cannot prove it with your incomplete method because maybe it loses too much precision, then you'd have this crossing situation, and then your certification with the complete method, that's why it's complete, because it's trying to explore all the combinations where crossing happens, right? Then it will get more and more expensive. Okay, so I hope this gives you a little bit of intuition, and that's really what is important for this lecture to get. So let's move on to the, we're just going to come back here to our example, mostly illustrating this point again here a little bit later. Okay, now let's, remember we had 4 steps. One was encoding the affine layer, which we looked at. It's a direct encoding, same way you can encode convolutions. Another one is to encode the REU activation layer, which we just saw how to encode that. And then let's encode now the precondition and the postcondition to complete our full encoding of the certification problem as a MIOP instance. So in our case, we're just going to look at the L infinity ball just for the example. But if you have some other more complex precondition, maybe some, the region is not just a hyperrectangle, but some other convex shape, you can encode it in a similar way here, just like we encoded the affine shapes. So what we have here, if we have the L infinity ball, right, with a radius of epsilon, what the constraints that we would generate in the case of the MIOP instance, we would say that, let's say for every pixel, right, every pixel is going to be in some range. So let's say that the original pixel value is xi, then some value, let's say 0.2, then some value of epsilon, then the new value of the pixel, let's say pixel I is like 50, like pixel 50, then x prime, which would be the pixel 50. So maybe we should have just put x prime 50 here just to make it even more clear, or x prime I. So the values that this can take is xi minus epsilon, the left side, the L, and then xi plus epsilon for the U. So you just generate a bunch of these lower and upper bound constraints for every pixel on the values on the left and right hand side of the interval. Okay, so this is very direct. So just for every pixel, you would actually have this constraint over here. So if you have 784 pixels, you'd have 784 constraints like this, one for every pixel. Okay, so this is fairly direct encoding as well. And now let's take a look at the encoding of the post condition, which is, it's essentially completes this encoding and lets us encode the verification or certification problem as an optimization problem, right? Let's see how that is done. So remember, this psi is just the post condition, right? So this is how the notation we were using before. Phi is the precondition, psi is the post condition, and the phi psi together define the specification. And so this psi, you know, what, let's say in the binary case where we had this simple network that we looked at before, you know, in the exercise, you can take a look at more, you know, multi-class classification, you know, more than binary classification here, maybe like 10 labels. But let's say we had 2 labels, and you want to say that you want to verify that label 0 is more likely than label 1. So the input would be classified to whatever label 0 stands for, maybe the digit 0 or some other thing that it stands for. So how would you do this? Well, what would you want to prove is that the output neuron, you know, O0 is greater than the output neuron O1, right? This would be the property that you would want to prove, right? And so this somehow must be going into our objective function. So this is the only place where the objective is modified, like is generated. So this would generate here the objective. And what would the objective be? What we'll try to do is to minimize the difference between O0 and O1, right? So essentially what we're trying to do is to find a counterexample to this. Potentially, you know, find some value where, you know, O1 is actually greater than O0. So if you find the minimal value here, we try to minimize the difference, and somehow O1 ends up greater than O0 or equal, then you would not be able to prove the property. So that's what we're trying to minimize the difference. So it's ultimately trying to you know, trying to maximize the value of O1 and try to minimize the value of O0. And in that way, we would you know, try to compute the minimal value here. Okay, so let's say that the MIP finishes, your MIP solver takes your MIP instance with this objective here, and it's done. Okay, so what do we check then? How do we have a certification check? Well, we just need to look at the, you know, the values that we get for O0 and O1, and then check if O0, because you know, we're trying to minimize this difference, and just check if O0 is greater than O1. So if O0 is greater than O1, you know, despite the fact that we try to minimize the difference, then yes, you succeed, verification succeed, and if otherwise, the verification fails. Okay. So this encoding lets us, you know, state a certification problem as an optimization problem. Okay. So now let's see how the entire end-to-end thing would look like. Okay, and so what would we get here is the following situation. So on the left here is the generic MIP instance. How would you state a MIP encoding, right? And this is what the MIP instance would be. And then on the right side is the, you know, this is on the left side is just the generic thing that the MIP solver takes as input. And on the right side is the neural network encoding, right? And so this was the objective that we were trying to minimize. We already discussed this just on the last slide. So this would be the mapping of the objective to be minimized. It would be stated like this, okay? O0 minus O1. If you have more labels, right, it would be just, you know, you have to think how would you, it's in the exercise. You can think how to actually state this. It would also be a similar minimization problem, except that it would involve more neurons, O0, O1, O9, for instance, if you're dealing with MNIST character data set. Okay, so this is just here for binary classification, but you can trivially extend it to you know, more than 2 labels. Here is the constraints, like this is the constraints that restrict our solution for the values for x1 to xn. And here where we would plug in the affine and the REU encodings, right? And so this is already we looked in the previous slide. So go over your neural network and just, encode the affine layers and the REU layers, and they would correspond to these restrictions over here. So the restrictions are just how your network looks like, just encoding your networks just like we saw before. Over here, these are some additional lower upper bound restrictions on the xi variables. And so in our case, we are going to have a couple of such kinds of restrictions. So one are the restrictions that we get from running the box certificate, the box analysis, using box to compute the lower and upper bounds for every neuron, and we just stick it in here. Okay, so at every layer P, we just take the all the neurons there, xi, and for every neuron xi, we just put the lower and upper bound. So this becomes, a number of constraints over here that we generate depending how many neurons are in this layer. And so this is for the essentially middle of the network, and this would be over here for the input to the network. So here is the L infinity example, but you can imagine other regions as well. So here we already looked at in the previous slides. This is just the lower and upper bound for every pixel. So this is how you would get box bounds for some of our xi variables. And so you would have variables for every neuron and for the inputs as well. Okay. And finally, we would have our integer variables, right? And this xj is here. This would be our integer variables, and aj, and these are like the used in our REU encoding, so they would be used, over here in this encoding. You'd get like ajs as we saw before. Okay, so this is again, on your left, your generic statement. On the right is how you encode your MIOP instance. This is how the structure looks like. Okay, so I hope that this is clear. And here we would plug in the encodings that we already saw before. And if you give this instance to a MIOP solver like Gorobi, then you'd see whether you can find values for O0 and O1 that satisfy your you're able, using them, you can prove you can solve the certification problem by checking whether O0 is greater than O1. If you're trying to prove that, that the input classifies to O0 or to whatever O0 stands for. Okay, so this is the encoding. So now let's look at our examples just to see what the encoding would look like. So coming back to our example over here, recall from the previous lecture that, right, these are the inputs for these are like the inputs for the, the 2 pixels, if you want, are the 2 input neurons, CX1 and X2, and some box ranges, some intervals of the same size. And over here is the bias, right, above each neuron. Here is an affine layer, one affine layer. Here is the REU layer. Here is the affine layer again, right? And here is the O1 and O0 and O1. So we are going to be encoding this network, right? So we took the network, we ran the box relaxation, we computed the lower and upper bounds here for every neuron, and then now we're going to be using this to encode the entire MIOP problem to try and prove that you indeed the values for O0 are always greater than the values of O1. And if you remember here, if you look at these intervals, when we were using just interval analysis, if you look at these ranges, 0.6 to 2.3 and minus 0.9 to 0.8, if you recall from the previous lecture, but you can also see it here, the intervals are actually, the intersection is non-empty. And so using just box analysis, the simple box analysis, we are not able to prove that O0 is strictly greater than O1. So this motivates us to try to use the MIOP, mixed integer linear solver, in hope that this indeed holds and we are able to prove it. Of course, it may not hold and then would fail, but maybe it holds and would succeed. Okay, in this case, it holds. Okay, but just the box analysis was too imprecise. So let's see now. let's take our network together with the box bounds and encode it using our encoding that we saw. So how would this look like? Okay, so let's see. Well, here we have the O0 minus O1 binary classification, and this is the affine layer. Okay, these are the two affine layers that we encoded. This one here, first affine layer, and then the second affine layer. And then we had one REU layer with two REUs here. So this is like, this is the one REU, and this is the other REU, and then we encoded just like we saw before. There isn't really any difference. We are just plugging here the values for the lower and the upper bounds that we got, before. So there really isn't much here except just plugging in the numbers, and the colors actually of light green should correspond to these constraints that we saw before. Okay, so we have the affine layer and the REU layer, and that's what you get. The input bounds are here on the input neurons here, right? X1 is in this range, X2 is in this range, and here are the pre-computed bounds that you get by running the box analysis, right? So each of these neurons, X3, X4, X5, X6 is bounded. We also have bounds on O1 and O0 and O1, but we're just not using it because we are trying to compute tighter bounds here with the MUP. Here, your binary integer variables. So you have as many binary integer variables as you have REUs, and they can, as you remember, can take the binary, so the value is 0 and 1. So this is your MUP instance, right? You can feed this MUP instance to your mixed integer linear solver, and it's going to be able to prove the property that O0 is strictly greater than O1 using all of these constraints that we have accumulated here. Okay. So let's see a little bit how, just to get an intuition, we already saw on this handwritten slide, but just on our example to get an intuition how the lower and upper bounds help again. Okay, so let's see over here, and to see why this box helps. Why does it help us to prune some of these instances? MUP solvers use a bit more elaborate algorithms, but this is the idea. You can actually implement the MUP solver yourself by using the results from the box analysis, or by using even a more precise convex relaxation, so the ones that we're going to be looking at later. So really what we have is 2 to the 2 cases. So we have A5, A6, so this is 4 combinations. But let's look at the first REU A5 and to see what happens over here. So if we consider the case that A5 is 0, what we're going to have is, if you do the simplification, we're going to end up with the following situation here. We're going to end up that X3 is X greater than X5 plus 0.1, right? If you put this on the other side, the 0.1 on the other side, and X3 is also less than or equal to 5, okay? And so what you can see here is this is actually an infeasible instance, right? So this is like an infeasible instance. And remember in our drawings before, well, this is clearly why, because this, in the A0 case, when A5 is 0, when A is 0, and the X is strictly positive like this, then this thing becomes unsat. This side becomes unsat, and you don't even have to consider it, okay, when A5 is equal to 0. Here we haven't expanded the A6 yet. The A6 is staying the same. We're just looking at the A5, right, in the case where A5 is equal to 0. So we don't even have to consider it here, okay? So this branch of A5 is equal to 0, we don't have to consider it. So here the box bounds, right? If we had these box bounds over here, okay, we actually don't have to explore further the values of A6. Okay, we don't care what the values of A6 are because the whole thing is unsatisfiable. Okay, so we are not even going to be generating these 2 cases for A6. I'm just going to stop and consider instead the value for when A5 is not 0, but when the A5 is 1. So here's how the box bounds help you here. Okay, so notice that even if you had computed tighter bounds for the X3, tighter bounds because there's an relatively not tight over approximation here for the X3. If you had tighter bounds, for instance, you had something like 0.5 to 1.1, then you'd still be unsatisfiable. Okay. So of course, if your bounds are very loose, your convex relaxation is very loose, like the box tends to be very loose, you may not be able to prove that this is unsatisfiable. For instance, if this is crossing over, it's like negative here, you'll not be able to prove, and then you'd have to explore the instance. But in this case, we can prove because x3 is strictly greater than 0. We can prove that. Okay, so let's consider the case where x is 1. Okay, so one thing to say here is, we don't even have to generate that case over there. We can just directly generate the case where the A5 is 1. So we don't even have to generate the case. Let's go back on the previous slide. We don't even have to generate this case where A5 is 0. You can just generate the case where A5 is 1. You don't generate this case again because the x3 is probably strictly greater than 0. And so you get an unsat instance here. So if you just look at the case where A5 is 1, you can just generate that and just not even deal with the variable A5. Okay, so just directly generate an instance where you only have A6 over here, and then deal with that case here. Okay, and we can do that, as I said, because using the box analysis, we know that x3 is strictly positive, so we don't have to generate this case A5 is 0. Okay, so now let's look at the case when A5 is 1, but A6 is 0 or 1. So let's look at the case where A5 is gone essentially. So now we only have A6 is 0 or A6 is 1. And so if we look at the case where A6 is 0, what we're going to happen is we're going to be coming over here where A6 was. Okay, and if we plug in the A6 being 0, we're going to end up with the following equations over here. You can do the simplification yourself from before. And then one thing here that you can do is, now we are interested in the case of, we're minimizing O0 minus O1. So we want to compute what this expression is. And we have some expression here for O0 and O1. And so what we want to do is to use these constraints over here, because, and these constraints over here for x5 and x6 in order to compute O0 minus O1. So look at what's happening here. We have, before we use x5, x6, let's look at O0 and O1. We have x5 plus x6 plus 0.5, and we have x5 minus x6 minus 0.5. So if we do O0 minus O1, you can just do the simplification here on this side before we even touch x5, x6. And so if you do that, the x5 are going to cancel out, and you're going to be left with 2 times x6 plus 1, 0.5 plus 0.5. So you're just going to end up with this constraint over here. Okay, so you're going to end up with this constraint over here. And then when you end up with this constraint over here, really, you just need to look, that's just a function of x6 over here. Okay, so you can look at x6 for the value of x6, and you know that x6 is 0. And then because x6 is 0, you're going to end up with O0 minus O1 is going to be equal to 1, right? And so if O0 minus O1 is 1, provably so, then you have actually proved, the minimum is always 1, right, of this difference here, no matter what. And so you have proven that the property holds. So in this linear programming instance that you generated here, this is a linear programming instance, there is no integer variables here anymore. A6 has been instantiated. You have proven that the O0 is greater than O1. A good exercise over here I have put, right, that you cannot just use the bounds for x5 and x6. So you have some bounds x5 and x6, right, for computing O0 minus O1, because, if you plug them over here, this will actually fail because this is not precise enough. Okay, you need to use all the constraints, which is what the linear programming will do, and compute this O0 minus O1 is 1 here. Okay, And so use all the constraints, and in this linear programming instance, which is this linear programming instance, this whole thing, you're able to prove that the property holds. But that's only one of the linear programming instances that would be generated here. Let's look at the other linear programming instance, which is the case where A6 is equal to 1. And so in the case where A6 is equal to 1, what we have is, if you do a simplification, you end up with something like that here. X6 is equal to X4 and X6 is in some range. Once again, we do the simplification over here. We end up with the same constraint as before. O0 minus O1 is this expression, just like before. Okay. But now, we have 2 times x6 plus 1, but we know that x6 is in the range 0 and 0.5, so you can just do the interval arithmetic here. And so that means that, O1 minus O2 is going to be 2 times the left side, which is 2 times 0. From over here, it's going to be 2 times 0 is 0, plus 1 is going to be 1, the left side, and then the right side is going to be 2 times 0.5. Because x6, the upper bound is 0.5, so you're going to end up with 2 times 0.5, which is 1, plus 1 is going to be 2. So provably so, O0 minus O1 is going to be greater than or equal to 1, okay? So the minimum of the difference is probably so 1. So for this linear programming instance over here that we generated for our from our MIUP instance, we have again proven that O0 is greater than O1. So in the case A5 is equal to, A6 is equal to 0, we have proven this, what we need. And in the case of A6 is equal to 1, we have proven what we need. And so we have actually proven that always, for all the linear programming instances that the MIUP can generate, O0 is strictly greater than O1, okay? Which is the property that we wanted to prove. And we used the box bounds to, to generate fewer linear programming instances. In the case where A5 is 0, we didn't proceed further because this is unsat no matter what we do with A6. And when A5 is equal to 1, well, we can then get rid of the integer variable and then just, because it's just going to be 1 there, there's no more branching going on after this, and then just consider the values for A6. So we really had to consider to invoke linear programming, if you like, on 2 instances out of the 4 possible ones by just using the bounds. And using these 2 instances that we are left, we're able to prove our property. Okay, so I hope that this gives you an understanding for how to encode a neural network certification problem as a mixed integer linear program, right? And then to use the corresponding MIUP solvers. It gives you an idea and understanding for how the information from automated analysis for even a simple convex relaxation like box can help you generate fewer linear programming instances, which is important because it is exponential in the certification will be exponential in the number of these linear programming instances which are generated because of the crossing ReLUs that we have, okay? So if you can prove that you're not in the crossing ReLU scenario using a convex relaxation like the box or some other relaxation, then you don't have to generate these splits and you get fewer instances to work with and potentially more scalable verification, being able to handle larger models, okay? Okay, so this was the idea of this lecture, to show you the MIUP encoding. How do you generate a MIUP program from the certification problem and the given neural network, okay? And this was an example of a complete certification, right? So you're just going to, at the limit, explore all of the linear programming instances that you generate, all of the possible splits of this A's. So nothing will be escaped, everything will be explored, right? Now, generally, because you have this exponential number of splits, in the worst case, this is quite expensive. And so hopefully you can use some of these incomplete methods that are fast and cheap to prune some of these instances, right? And so this was an example of using, this is a typo here, it should be using an incomplete method to speed up a complete method, right? So using the box domain abstraction to speed up MIUP. Now here we saw one of these combinations of convex relaxation, like box with MUP, but there is actually other combinations. You can actually use it in the other direction. You can use the result from the MUP solver in order to obtain more precise results for convex relaxation analysis, like incomplete methods like box, which we'll look at some of the later lectures. Okay, so I hope that you enjoyed the lecture, and there is exercises that we're going to study this problem with various examples in more detail so that you get a better understanding. So I hope you got an idea how to use MUP to encode neural network certification problems. And great, so yeah, see you next time.